Okay, under electricity, we will study electric field, capacitance, AC circuit, topic 21. Right? AC circuit can be electricity, can be magnetism, both. Under electric field, we'll study electric field and field lines, uniform electric field, force between point charges, electric field of a point charge, electric potential. So basically, we are study quite similar to gravitational field. 18.1, 18.2 used to be under AS. Since 2022, it has been combined with A2 work. These are A2 work. Then AS no more. Don't worry about, you can use your textbook. I know what are the things that you can find. Right? Likely the G, you're likely to use that. And then this permittivity of free space. Right? This is a value of K given. And this formula is given. When they use the term use, it means they want you to know how to use it. No need to recall. They will give you the formula. Okay, electric field and field lines. Understand that an electric field is an example of a field of force, and define electric field as force per unit positive charge. Recall and use. Right? That means you must remember this formula and know how to use it. The force on the charge in the electric field represent the electric field by means of field lines. Page 109. Okay, let's just review. Right? Under AS, you study that the nucleus is the massive part of the atom, and in it you can find electron is found in the electron cloud. Proton and neutron can be found in the nucleus. Proton is positively charged, same charge as electron, except different mass. Right? Neutron is neutral. So in a neutral atom, number of proton equals number of electron. Electrons can be removed. Right? We call ionization. For a neutral atom, leaving an atom now called an ion with a net positive charge. Atoms may also acquire excess electron and become negatively charged ions. Stop me if you want to ask question. Contact forces are what we have studied so far. Forces act where bodies are in contact. Right? Friction and tension, where the block and the table are in contact. There's friction there. Right? If there's no contact, no friction. Same like here. If the bob is attached to a string, this is contact force, then there's tension. Action at a distance. Whereas you come to electric force, they are action at a distance. Right? The balloon is charged negative. This balloon is charged positive. They attract each other even though they don't have any contact. Object experience a force when they are at a distance from the other object. That's what it means by action at a distance. No contact, but they feel the force. Electric force is action at a distance. Force. A charged balloon can have an attractive effect upon an oppositely charged balloon even when they are not in contact. The two balloons, one negatively charged, one positively charged, they attract each other even though they are not in contact. Electric force act over distance separating the two objects. Well, you can see that as they move nearer, the diffraction becomes greater. Right? No contact. Consider a physics demonstration in which a charged object is brought near the plate of needle electroscope. Prior to any contact between the electroscope plate and the charged object, the needle of the electrode begins to deflect. Right? As it comes nearer and nearer, the deflection becomes greater and greater because the force becomes stronger and stronger. The charged object exerts an influence upon the charged electron. Right? It's negatively charged, so it repels the electron. Electron occur on the leaf and here on the charged electron in the electroscope, even though physical contact is not made, the charged object of affects other charged object which will in the neighborhood, right? The balloon is charged, so it affect neighborhood, right? Charges in the surrounding neighborhood, surrounding. Around a charged object is an electric force field, right? Because around the negative charge balloon, there's a electric force field around there, a force field. Like charges repel and opposite charges attract, or unlike charges attract lah. Electrons may be removed from a neutral atom, leaving the atom called ion with a net positive charge. Atoms may also acquire excess electron and become negatively charged ions. Right? So unlike charges or opposite charges attract, like charges, negative and negative repel, positive and positive repel. Right? This is just to illustrate the force field. Force field is a space or region where a force is experienced by a particle placed in the field. Right? If there's a presence of a force field, you place a particle there, the particle will experience the force. So if it's example, if it's an electric field, you place a charge, the charge will experience a force. Right? Just like that. Put a particle there, particle will experience a force. Right? If there's a force field. A charged object creates an electric field around itself. It's charged there, positively charged. Right? It creates a field around itself. Right? You cannot see it, but it's infinite. Right? You can think of an change, an alteration of the space in the region which surround it. Right? It changes the region around it. We can represent the field by field lines or line of force. How do we show the line of force and measure its strength? Right? Roughly indicate the strength of the field. What is meant by isolated point charge? There's no others, only by itself. Right? So that is the field of an isolated point charge, positive charge. Arrow on the line show the direction of the acceleration or force on the positive charge. Right? So direction is the force on positive charge. So you put a positive charge there, the positive charge will move in the direction of the line. Electric field flows away. It's just like water flowing. Right? Electric field is like water. It flows away from the positive charge. Right? Where it's closer, the lines are closer together, the field is stronger. Just an indication. You cannot calculate it, but an indication. Where the lines are further away, it's weak field. Right? So this is the field due to an isolated negative charge. Electric field points towards the negative charge. Right? The line behave as it is, we can think of it as they repel each other sideways. So they are as far away from each other as possible. So electric lines of force between the positive and negative charge. Line of field are continuous line that always run parallel to the electric field. So basically, it tells us that if you put a positive charge here, the positive charge will move along that direction and come back here. Right? If you put a positive charge here, it will go there, take a big arc there, and come back there. They act like lines of flow, right? Like water flowing away from the sources on positive charge into the sink of negative charge. So they flow away from the positive charge, enters as a negative charge. How does fuel line act? Fuel lines do not intersect, right? They don't cut each other. Fuel lines are close together when the magnitude is large and vice versa. So we can see that and fuel lines are closer, is stronger fuel here, further away, weaker fuel here, right? Or weaker fuel here. Fuel line starts on the positive charge and end on a negative charge. They are continuous in between, right? It's a continuous line, no break in between. Right? Fuel lines look like flow patterns. The strength of a field is represented by the density. We are just repeating the number of lines, density of the lines. That's the number of lines passing per unit area. Right? Per unit area is closer, stronger field, weaker field. Number of lines passing per unit area is smaller. Right? Same here. We can see from here straight away that this is a more charge here on the charge sphere C. Right? The lines closer together and less charge here on the sphere A. So these are few lines due to a positive charge. There's your Earth there. And then this is a parallel plate conductor, which you'll study in a while. So this is a few lines due to positive charge. To positive charge, they try to, the line feel like they are repelling each other. Each other. What's the line of force? A line of force, memorize this one, no choice. A line of force in an electric field is a tangent to the line. Cambridge like to use a line tangent to the line rather than curve right? It's a curve, right? But it's not a line. But that's what they do in the question paper also. They call it a line, so be prepared to accept it's a curve also. Give direction of force on a small test positive charge. Right? The arrow show where the positive charge will move. What does the arrow on the field line shows? Direction of force on a test positive charge. So you put a positive charge here, a test positive charge here, a small positive charge here. The direction of the force. Right? Tangent to the curve. Right? It's just repeating just to show you. Right? Stronger force nearby here, weaker force, weaker field further away. And then if you are required to draw the few lines there, it's just a tangent to the curve. Here, tangent to the curve, arrow will point like here. Okay, so it's good to summarize the things that you need to remember. Force field, line of force, and then we will define how to measure the electric field strength. Okay, charge conductor. This is positive charge conductor, negative charge conductor. Electric field is zero inside the conductor. Electric field is zero inside the conductor. The charge appear on the surface. Same here. No electric field inside the conductor. Right? If there's electric field, the charge will move. So there's no electric field there. charges in a conductor repel each other so that they are as far away from each other. Right? On the surface, they are as far away from each other. The charge reside on the surface. The field line leave and enter the surface at right angle. Direction of field lines at any point is the tangent to the curve. Field lines appear to originate from the center. Right? Leave at the surface, leave at right angle, and then you produce backwards, it goes to the center. Same here. It enters the surface at right angle, and then it continues towards the center there. I see the charge is concentrated at the center here. Same here. See the positive charge concentrated at the center there. Right? If you're interested at this point there, then it's just direction of the electric field. That's the direction of the electric field. Okay, same as point charge. If it's, this is called uniform electric field. Right? Lines are parallel and equal distance apart. These are non-uniform field. Lines are not parallel. Okay, let you absorb before I carry on. Okay, next point, we are interested to measure the strength. So far, the lines indicate strong field or weak field. Right? We define electric field strength, memorize force over positive charge. Right? In symbol, E equals F over Q. So we have a charge there. Right? We want to find the strength of this charge Q. This charge Q creates a field around it. So you want to find the strength of this field created by this charge Q, capital Q. Right? So we put a test charge there, a test positive charge. Right? How we define force per unit positive charge acting on a stationary point charge. Place a test charge Q and find the force on it. So that definition tells us to find the force and place a charge. That's a test charge, remember, not discharge. Right? Discharge creates the field. So we put a test charge there, a test charge here. You want to find the field here? Put a test charge here. Find the force on this test charge, and then use this equation to find the electric field strength at that point. Okay. Where did Mr. Sauce teach you all by now?
By now it's simple harmonics.
Say again.
Simple harmonics.
Oh, so you got a long way to go lah, because you still have to teach you paper 5. Okay, memorize this equation. Right? Remember, examiner can try to test you. This is the one that creates the field. If you want to measure the field due to this charge, we place a test positive charge here. All we need to do is find the force on this test charge and divide by the charge. That's what the equation tells us to do. Unit, right? Electric field strength is denoted by a symbol E, is a vector. Then the equation can be rewritten in symbolic form. Right? As a formula. Force is in Newton, charge is in Coulomb. This is Newton per Coulomb. Right? You can show it's volt per meter also. Right? Day 2, you're not interested in unit. You're not interested to derive the unit, but you need to remember the answer lah. If sometimes they don't give you a unit, you're supposed to write down there. It's worth 1 mark there lah. But you won't be asked to show what's the unit of electric field lah, like AS lah. The next definition allows us to determine experimentally the electric field at any point in an electric field. all we need to do is all we need to do is place a test charge at the point of field. Right? Like here, you're interested, place a test charge here, find the force, and then use the formula. Right? Use the formula for divided by charge. Right? Now these two charge. Okay, these two charge. The field due to these two charge. You put a test charge there, small q, and then find the force on the test charge. Okay, force on a charge in electric field. For charge q, right, the charge q placed in electric field or electric field strength. If you are given the electric field strength E, and there's a charge there, you place it, the test charge there, and the force is just F equals to QE. Right? From the definition, we just cross multiply. Right? Cross multiply there. Is given, you can find the force. Direction of force is the direction of the field. Right? We choose a positive test charge, and this direction is the force on the positive test charge. So the force on positive charge will be the same direction as the electric field direction. Right? This formula you need to recall and use. Know how to use it? Memorize it. Right? For the electron, the force is repulsive, so it's in the opposite direction. Magnitude is still the same. Right? If the charge is still the same, except we put a negative charge, because we choose to the right as positive, to the left is negative. Any comments so far or anything to clarify?
No.
Okay, let's carry on. 18.2, uniform electric field. Right, it's supposed to recall and use this formula. Calculate the electric field strength of a uniform field between charged parallel plates. Describe the effect of a uniform field on the motion of charged particle. It's a review of your AS work. They won't ask you, but you need to remember and know how to use it. Right? That's definition of potential difference. Right? Work done, divide by charge that you take. Right? That's definition for 1 volt. Right? It's just a revision. Chemical for dry cell, chemical reaction in the cell causes the charge to separate. Right? It's positive terminal, there's negative terminal, there's a symbol for the cell, and there's a symbol for many cell, more than one cell. Right? So it's the battery. Positive terminal of the cell is positively charged. Negative terminal is negatively charged. Right? Parallel conducting plate, or sometimes we call it capacitor lah. Right? There's your battery. The positive terminal of the battery is positively charged. Right? Positive terminal, positively charged. So this is wire. So this wire will be positively charged. This terminal is negatively charged. So this one, electron will be appear here, negatively charged. Right? So we put conducting plate, parallel conducting plate, and then there's an insulating layer, usually it's air. Right? So electron will come here, electron come here, will repel an electron from here, the electron will flow back to the positive terminal. Another electron comes here, repel an electron, electron will flow back. So when is finally the potential difference between these two plates is the same as the battery. Right? All these positive charge evenly spaced, negative charge evenly spaced. Parallel plate capacitor is made of two conductors separated by a thin layer of air, insulating layer of air. When a battery is connected, That one we have explained already. We have a battery connected to the plate there. Electron will come here, repel the electron will go back to the positive terminal and carry on until the potential difference across the plate is the same as the battery. That's how it looks back in 3 dimensions. There's a conducting plate, one with positively charged, one negatively charged, and then we call it dielectric. Right? Usually, you don't need to know too far. For yours, you are interested in either this a vacuum or air. Not interested in water or anything else. Right? So if it's anything other than air, then we use epsilon. The charges are evenly spaced. They repel each other so that they are evenly spaced. Total charges on the bottom and upper plate are the same. Charges upper plate, because charges on the lower plate is the same. Right? So few lines start from positive and end on a negative charge. So they are parallel and evenly spaced. So the field are uniform. Between the plate, the field is strong, uniform, and perpendicular to the plate. The lines start from positive charge and end on a negative charge. The lines are evenly spaced. Keep that in mind. What does it mean by even uniform field? The field is uniform within the plate. It means that at any point between the plate, the magnitude and direction is the same. Now you take a point A here and a point B there. The field is actually the same in magnitude and direction, pointing downwards there, pointing downwards there. Right? The upper plate is V1, bottom plate is V2. Don't worry about sign effect. It's just in case you have to encounter in your textbook. As far as you're concerned, these are parallel. At the edges between the plates, the field is non-uniform. We normally take the field between the plate as uniform in calculation and neglect the edge effect. E point towards the lower potential. Higher potential, positive plate, lower potential, negative plate. So don't worry about this edge effect. It's called edge effect. Right? Non-uniform. Uniform is where they are parallel, equidistant apart. It's just like the gravitational field near the Earth's surface is uniform. You draw an object, it will move downwards. Near the surface of the Earth, the gravitational field is uniform. An object placed near the surface would accelerate to the surface of the Earth, right? Because the force attract this object, so it will accelerate downwards. Or we can think of it as object move from a higher potential to a lower potential. Right? So we can use delta V or V potential across the plate. So it's positive plate, potential of positive plate minus potential of negative plate. D is the separation. Right? Your syllabus use delta D. It doesn't matter the symbol used, as long as you know what is the meaning. Right? If we think in terms of force, at 10 minutes time we have to stop. Make sure you try the worksheet while you wait for the 50 minutes or so. Right? There's no shortcut. Try the worksheet. Okay, the upper plate has a high potential. Lower plate has a low potential. The positive charge placed near the upper plate, positive charge placed near the upper plate, experience a repulsive force. If we think in terms of force, then it experiences a repulsive force. and accelerates to the lower plate. You can think of it as like charges repel. That's the direction of acceleration or direction of the repulsive force. Or we look at energy, right? Positive plate, high potential, negative plate, low potential. Positive plate is at a high potential. Right? So another way of viewing it is to say that the positive charge move from a higher potential to a lower potential. Whereas electron near the lower plate will move from a lower potential to higher potential. Right? Or we can think of it as the force is repulsive. So it accelerates upwards there. Relationship between E and delta V. Right? This you're not required to derive. Right? Not required. I just show you just for info. Right? There's a potential difference between the plate. There's the electric field. There's the charge there. So that charge will experience a force. The force can be calculated by E electric field times the charge. Then if it's required to move from the upper plate to lower plate, the work done is force times your distance. And then replace our F by EQ to get that. Since the potential is defined as, that's the definition for potential, work done divided by the charge that we move, this charge that we move. So EQ, okay. So that's the formula we have got. Know how to use it and memorize it. Magnitude of electric field strength or parallel conducting plate is the potential difference divided by the separation. Right? V1 is higher potential, V2 is lower potential. You're required to recall and use this formula. Okay, how does the graph look like? Taking upper plate as positive, that's the origin of X. And then taking downwards as positive, right? We say the electric field strength is constant, so it's a horizontal line. No? Right? Remember, the plate is fixed. We are looking at the electric field between the plate. As we move from top to bottom, there's our x-axis. How about the electric potential? Potential difference between the plate. Right? We take at a distant x, the potential difference is V. So we use a formula that we have just derived. Right? V1 minus V equals to E times D. D is our x, that distance. There's your V here. So we rewrite that equation. There's your V. There's your x. So it's a straight line graph with negative gradient. Any comments so far?
No.
Okay. Right? And from the potential difference graph and separation graph, E, we can get the E as a gradient of this straight line. Right? So summarize for you, right? What we have learned. The next part, we are going to look at the motion on the charge here. Okay, let's try some question in the worksheet, page 116. You may not have chance to try all of them, but you carry on with the question. We still got about 4 minutes. This one you can. Do you need my PowerPoint slides?
Um, I think I'll get them in the future. Not for now.
Okay, if you want it, you tell me. If not, I won't send you. I just send you the notes
Yeah.
because it can get too confusing. Okay, try this question. Try this question. Use the formula that I've given you. F equals to EQ. That's your charge. Positive charge. Electric field strength is given. What's the magnitude of the instantaneous force on the charge? We should be able to calculate out. Right? F equals to EQ. 120 is E. And then there's the charge. Convert to SI unit. Calculate out. Where's the direction of the force?
Onwards.
Downwards. Parallel to the electric field. Okay. How about for the electron? Where's the direction of the force?
Uh, Measure of force.
On the electron. Where's the direction of the force?
Upwards.
Okay, good. That's why it is upwards. Right? Try to calculate this one. Electric field strength. You are given the magnitude of the force and the charge is given. So what is the electric field strength? Play with the formula only.
F equals to Q.
E equals to F over Q, that's all. Right? Get you familiar with the formula? How to calculate?
Yep.
Direction of the force is parallel to the field. This is more challenging. In case we get cut off, you can try it out. A pair of parallel conducting plate is connected to a constant PD source. Sketch the graph to show how the electric field strength varies with separation between the plate. Right? Don't get confused. Just now we look at the plate is constant. We look at the field and the potential within the plate. Now, the plate is connected to a battery, the constant source. Now we are moving the plate apart. So how does the graph look like? Potential difference against separation. How will it look like? Yep.
Increasing.
No. Connected to a constant PD source. So you cannot
Oh.
change the PD source. You move the plate, the potential difference is still the same. So it's horizontal line.
Oh, yeah, yeah.
Right? How about the electric field strength against separation? You have to use the formula, play with the formula. Right? Use this formula. V is constant. Right? That's your D, that's your E. Okay, can.
Yeah, can.
Okay, we cut off at any time now. Don't worry about this one, it won't come out. This one is AS work. Can try this one. It won't come out to calculation because it involves a lot of mathematics, and that's not what they want. Right? This tested in AS, but you should be able to find the magnitude. I think I'll leave you to try it out and try the others.